Now that we've seen the basic idea of case analysis and the destruct tactic, let's see how it relates to our logical connectives. So in this and in the next few videos, we'll be talking about destruct, case analysis, and logical connectives. In this video, it'll be conjunction. In particular, we've seen that you can use split to prove a conjunction. The way you prove a conjunction is, well, to get A and B, you prove A, you prove B, and split lets you sort of split your goal to do those two parts together. What if you know A and B? How do you use the fact that you know some but not all of it, right? So if you know A and B but you only care about A, how do you get the A out? How does that work? So destructor case analysis is the way to do it. So here, let's look at this first lemma, proj 1. Let's take a second to see what it says. Here it's saying for any propositions P and Q, if you know P and Q, then you know P. Seems intuitive to me, right? If you know P and Q, then certainly knowing P is part of it. What would a proof of P and Q have looked like? Well, you would have said split and then proved P. Okay, so that proof is in there somewhere, right? Someone at some point knew how to show P. So here I've written this the way I would write it, where I use this nice as pattern, this nice sort of pattern as we saw for destructs before, and I just throw it in my intros and say, yeah, could you break it up for me? But let's break it down a little more slowly. Maybe you would do something like this, right? We start out with P and Q, and we get the hypothesis H such that P and Q. So we could just destruct H. If we leave off the pattern, Cock will choose names, and unsurprisingly, Cock did a bad job naming things. So let's add our pattern. Much better. Now at this point, our proof is made, right? We need to show P. We know P and HP. Good to go. So this proof is great. I like this proof because it's shorter, and also because whenever I see a conjunction, oops, okay, get rid of the H. Whenever I see a conjunction, I'll basically dispatch it as soon as is reasonable. Right? It's just going to be useful to have the subparts. Occasionally that bites you, right? If you wanted to prove the conjunction that's the same on the other end, well, you shouldn't have broken it apart. But you can always reconstruct it at very low cost. You just say split and then prove the parts and you're good to go. Okay, so much for that proof. Here's an interesting property of and. It's commutative. If you know P and Q, you know Q and P. So this is a nice showcase of sort of like everything that you can do with a conjunction. We'll take one apart, we'll build one. So we have that same intros pattern. We know HP, we know HQ, proving P and Q respectively, and we need to show Q and P. So the way you prove a conjunction is with split. Great. We do the left-hand side first. We've got to show Q. Well, we've got that in HQ. Okay, now we need to show P. Well, we've got that in HP. Lovely. All right, so you have an exercise where we've actually filled in the as pattern for you. I wanted to highlight this nesting, right? Because what's really going on here, let's take a look, is H is this thing. So Cock's going to print it nicely because sort of by default, conjunction is going to be right associative. But this is sort of in secret parentheses that Cock isn't printing for you. So if we just said destruct H as HP HQR, you'll notice that, okay, we haven't destructed it all the way. So then we would need to say something like, okay, well, destruct HQR as HQ HR. Now, these patterns nest is the thing I'd like to have come across. So we can actually just say something like this. And that does it all in one go. Okay, but at that rate, well, then why intros H only to destruct it? Cruel, really. Just break it up at the front. Right, so this nested pattern works nicely. Right, if you forget the nested pattern, Cock will give you some sort of like mildly cryptic error message here. Let me make this a little larger for you. Unexpected name. At most, 2 introduction patterns were expected in the branch. Basically, and is a binary operation. It doesn't want a bunch of names there. It wants exactly 2. Now, if you wanted to keep destructing, keep doing more destruction there, that's fine. One thing I want to note here is like, look, we did 2 destructs with this as pattern, but we still only have 1 subgoal. And that's because of the nature or the structure of conjunction. Conjunction, there's only one way to build a proof that say P and Q or that Q and R. It's to have both of those things. It's not like a base where there's 4 different cases you could have, or like a natural number where there's 2 different cases you could have, or like a Boolean where there's 2 different cases you could have. There's only one proof of any conjunction, a proof of its parts. Okay, so you'll have to finish this proof as your homework. I want to finish up with just sort of an example with non-abstract propositions. So let's start here. for any natural numbers n and m, if n equals 0 and m equals 0, n plus m equals 0. Let's do it the slow way. Get n, m, and h. Destruct h as, and I don't want to let Cock name this. I'm going to come up with my own names. hn, hm. You can call these en, em. Again, you're really free to choose these. I think choosing good names is good, but it's up to you. But at this point, looks pretty good to me. Let's just do some rewriting. All right, and then fortune favors the bold. I'm not even going to simple. Let's go. Oh, what beauty. Okay, now here's the next version of it where you just write the pattern. Right now here, okay, we're leaving off the arrows. Maybe not the greatest style, but all right, I like it. Works for me. Okay, lastly, you might wonder like what's with the and here? Why didn't you write it this way? Prof Greenberg, you said that like multiple arrows like this acts like an and, so like why didn't we just do that? You know, you're right. If I were to write this theorem myself, I would almost never write conjunction as sort of a premise. I would write it out this way. It ends up being easier to use in Coq for a number of reasons. Uh, So that's true. In this setting, this seems much easier, right? There's no pattern. You just let it go, right? The proof's the same. You love to see it. But it turns out that like in the middle of a proof, it might come up that you get a conjunction from some other reason. So like conjunctions in inputs or outputs of implications can arise for more complicated reasons than somebody literally wrote them there. So you do need to know how to deal with it. Okay, that's enough for conjunction. Next video I'll do disjunction, and then we'll move on and talk about some other interesting logical connectives. Cheers, y'all.